At 11:47 a.m. on April 18, 1942, Second Lieutenant Sarah Chen crouched over her navigation table in the cramped nose of a B-25 Mitchell bomber 400 miles west of Tokyo, watching her compass needle spin wildly in circles. The magnetic storm that meteorologists had failed to predict was scrambling every navigation instrument aboard 16 aircraft carrying America's most daring raid into the heart of Japan. The 24-year-old navigator from San Francisco had trained for 2 years using the most advanced navigation equipment the Army Air Forces could provide. Now, with enemy territory approaching and fuel running dangerously low, none of it worked. Her pilot, Major Jack Morrison, called back through the intercom. "Chen, I need a heading. We've been flying blind for 30 minutes, and I can't see anything but ocean." Behind them, 15 other B-25s were following Morrison's lead aircraft, trusting that someone in the formation knew where they were going. Radio silence was mandatory to avoid Japanese interception, so Sarah couldn't communicate with other navigators to coordinate their position-fixing efforts. Sarah stared at her useless instruments and felt the weight of 16 crews depending on her calculations. The Doolittle Raid was supposed to demonstrate American resolve after Pearl Harbor, showing the world that Japan itself could be bombed. But if the bombers missed their targets and crashed into the Pacific, the mission would become a propaganda disaster that could affect the entire war effort. Everyone expected her to fail. During training, instructors had questioned whether a woman could handle the pressure of combat navigation. Squadron commanders had suggested she might be better suited for administrative duties. Even some crew members had privately wondered if she could be trusted with their lives when the mission turned dangerous. They were about to discover what happened when you underestimated someone who understood mathematics better than anyone else in the formation. Sarah Chen grew up in San Francisco's Chinatown, where her father operated an import business requiring precise calculations for international shipping. By age 12, she was helping him calculate tonnage rates, currency conversions, and delivery schedules that had to account for weather delays and route changes. Mathematics wasn't just academic in the Chen household. It was a practical tool for solving real-world problems that couldn't be approximated. Her mathematical talent became apparent during high school, where she consistently scored perfect marks in calculus and trigonometry courses that challenged students planning engineering careers. Stanford University offered her a scholarship in 1936, making her one of fewer than 24 Chinese-American women enrolled in the mathematics program. At Stanford, Sarah specialized in theoretical mathematics with a focus on spherical trigonometry and astronomical calculations. Her senior thesis involved developing improved methods for celestial navigation that could account for atmospheric refraction and magnetic declination errors. The work was purely academic, designed to explore mathematical principles rather than solve practical navigation problems. But Pearl Harbor changed everything. The Army Air Forces desperately needed navigators who could guide bombers across thousands of miles of ocean to targets deep in enemy territory. Sarah enlisted in January 1942, expecting assignment to training duties or administrative work that would keep her away from combat operations. Instead, she found herself selected for the most dangerous navigation mission in military history, a secret bombing raid against Japan requiring flying 2,000 miles over open ocean with no navigation aids beyond what individual navigators could provide using their own calculations and instruments. The selection wasn't based on confidence in her abilities. It was based on necessity. Mission planners needed the best navigators available, regardless of gender or ethnicity. Sarah's academic background and mathematical expertise qualified her when more traditional candidates weren't available in sufficient numbers. Training began at Eglin Field in Florida, where 16 B-25 crews practiced specialized techniques for carrier-launched bombing missions. The bombers would take off from USS Hornet, fly 650 miles to Japan, bomb assigned targets, then continue west to Chinese airfields for refueling before returning to base. Navigation requirements were unlike anything previously attempted in military aviation. The bombers would fly at low altitude to avoid radar detection, making astronomical navigation difficult. Radio navigation aids would be unavailable due to radio silence requirements. Dead reckoning navigation would be complicated by unknown wind conditions and possible course corrections to avoid enemy interception. Sarah spent weeks calculating flight plans, accounting for every variable she could identify. Fuel consumption rates at different altitudes and power settings, wind patterns based on seasonal weather data, magnetic declination variations across the flight path, and backup routes if primary targets were inaccessible due to weather or enemy action. But her calculations assumed basic navigation instruments would function normally. She had backup plans for equipment failures, alternative routes for unexpected weather, and contingency procedures for enemy interception. What she hadn't planned for was a magnetic storm, powerful enough to render every compass and radio direction finder useless while flying over featureless ocean hundreds of miles from the nearest landmark. The mission launched from USS Hornet on April 18, 1942, earlier than planned, because Japanese patrol boats had detected the carrier task force. Instead of launching 400 miles from Japan as originally intended, the bombers took off 650 miles from targets, adding significantly to navigation challenges while reducing fuel margins for the flight to China. Sarah's bomber was designated lead aircraft for the formation, meaning her navigation accuracy would determine whether 15 other crews reached their targets or flew aimlessly over the Pacific until fuel ran out. The responsibility was enormous, worsened by radio silence, preventing coordination with other navigators who might have different position estimates. For the first 90 minutes after takeoff, navigation proceeded according to plan. Sarah's compass readings were consistent, her dead reckoning calculations showed the formation on course for Tokyo, and her estimated arrival time aligned with the mission schedule. Weather was clear enough for occasional celestial observations that confirmed her position estimates. Then, at 11:47 a.m., everything went wrong simultaneously. Sarah's compass began spinning erratically, the radio compass pointed in random directions, and the backup magnetic compass showed readings differing from the primary instrument by more than 40 degrees. A magnetic storm of unprecedented intensity was affecting every electromagnetic instrument aboard the aircraft. Modern meteorology would have predicted this event, but 1942 weather forecasting couldn't anticipate magnetic storms with sufficient accuracy to warn military operations. The phenomenon occurred when solar particles interacted with Earth's magnetic field, creating temporary distortions that made compass navigation impossible across large geographic areas. Sarah realized immediately that traditional navigation had become useless. Her carefully calculated flight plans assumed functional compass readings for course corrections and position fixes. Without reliable magnetic bearings, she had no way to determine the bomber's heading or confirm its position relative to the target area. But Sarah had spent 4 years studying mathematical solutions to navigation problems not covered in military training manuals. Her Stanford thesis had explored celestial navigation techniques that didn't depend on magnetic instruments, using astronomical observations and mathematical calculations to determine position and heading without compass references. The techniques were theoretical, designed for academic study rather than practical application. No military navigator had ever attempted to guide a formation of bombers using pure celestial navigation while flying at combat altitudes through potentially hostile airspace. The mathematical requirements were enormous, observational challenges were severe, and the margin for error was essentially zero. Sarah made a decision that violated every navigation procedure she'd been taught. She would abandon instrument navigation completely and guide the formation using astronomical observations and mathematical calculations performed manually during flight. The theoretical foundation for celestial navigation dated back centuries, but applying these principles under combat conditions required adapting classical mathematics to unprecedented circumstances. Sarah would need to perform calculations that normally took ground-based navigators hours to complete, doing the work in minutes while flying through turbulence in a combat aircraft approaching enemy territory. The mathematical challenges were staggering. Each celestial observation required determining the exact time of the sighting to within seconds, measuring angles between celestial bodies and the horizon to within minutes of arc, then performing spherical trigonometry calculations that involved logarithms, trigonometric functions, and coordinate transformations that most mathematicians would find challenging under ideal conditions. Sarah had to work entirely from memory, since the mathematical tables normally used for celestial navigation weren't available aboard the bomber. She'd memorized the most critical values during her Stanford studies, but the calculations still required manipulating five-place logarithms and complex trigonometric relationships while bouncing around in an aircraft flying toward combat. The first requirement was determining the bomber's exact position using celestial observations. Sarah climbed into the nose turret where plexiglass provided better visibility for astronomical sightings. Bringing her sextant, chronometer, and mathematical tables she'd smuggled aboard despite regulations limiting personal equipment. The nose turret was cramped, cold, and offered limited workspace for the precise measurements required for celestial navigation. Sarah had to brace herself against the aircraft structure while using the sextant, compensating for the bomber's movement and vibration that made precise angular measurements extraordinarily difficult. Using the sextant through aircraft windows was nearly impossible under normal conditions. Air turbulence made precise measurements difficult, while the bomber's speed created parallax errors that affected accuracy. Sarah had to compensate for aircraft movement, account for atmospheric refraction, and correct for the difference between apparent and true horizons while flying 200 feet above the ocean surface. The observational challenges were compounded by the need for absolute precision. A single degree of error in measuring celestial angles could place the bomber more than 60 miles off course. At their current speed and fuel consumption rate, navigation errors of that magnitude could mean the difference between reaching Japan and running out of fuel over the Pacific. But the biggest challenge was performing mathematical calculations required to convert astronomical observations into geographic coordinates. The process involved spherical trigonometry computations that normally took trained navigators 30 minutes to complete using specialized tables and mechanical calculators. Sarah would have to perform these calculations in her head while bouncing around in a cramped bomber flying through turbulence toward enemy territory. The mathematical complexity was enormous. Sarah needed to calculate the Greenwich hour angle for each celestial body she observed, determine the body's declination at the exact time of observation, apply corrections for atmospheric refraction, account for the height of eye above the horizon, then solve the spherical triangle formed by the observer's position, the celestial body, and the geographical position directly below the body. Each calculation required working with multiple coordinate systems simultaneously. The horizontal coordinate system, based on the observer's position, the equatorial coordinate system, based on the celestial equator, and the geographical coordinate system used for navigation charts. Converting between these systems required understanding the mathematical relationships that governed spherical trigonometry. Sarah had memorized most necessary mathematical tables during Stanford studies, but she still needed to perform complex calculations involving logarithms, trigonometric functions, and coordinate transformations while maintaining accuracy to within minutes of arc. A single computational error could place the formation hundreds of miles off course. The computational work required extraordinary mental discipline under extremely stressful conditions. Sarah had to maintain perfect concentration while performing mathematical operations that would challenge most people under ideal circumstances, doing the work while flying in a combat aircraft through increasingly hostile airspace, where enemy interception remained a constant possibility. She began with solar observations using the sun's position to establish a rough north-south line of position. The calculations required determining the sun's exact coordinates at observation time, correcting for equation of time variations, accounting for observer motion during the sight, then solving for the line of position that intersected the aircraft's geographic location. The sun's position in the celestial sphere changes continuously as the Earth rotates, requiring calculations that account for the exact time of observation. Sarah had to use her chronometer to record the precise Greenwich mean time of each site, then calculate the sun's Greenwich hour angle and declination for that specific moment. The Greenwich hour angle calculation required knowledge of the sun's mean longitude, the equation of time correction for the date, and the local hour angle based on the observer's estimated longitude. Sarah performed these calculations entirely from memory, using mathematical relationships she'd memorized during her academic studies. Atmospheric refraction complicated the observations by bending light rays as they passed through the atmosphere, making celestial bodies appear higher above the horizon than their true positions. Sarah had to apply refraction corrections based on the observed altitude, atmospheric pressure, and temperature conditions that affected the refraction index. The work was extraordinarily difficult under combat conditions. Sarah had to brace herself against aircraft movement while taking precise angular measurements, record exact timing for each observation, then perform calculations requiring manipulation of five-place logarithms and trigonometric functions entirely from memory. The mathematical work required was far beyond what any military navigator had ever attempted under operational conditions. Sarah was essentially performing the functions of an entire navigation department using only her knowledge of theoretical mathematics and a sextant she'd brought from her Stanford studies. But mathematics had always been intuitive for Sarah. Where other navigators relied on mechanical procedures and published tables, she understood underlying geometric relationships that governed celestial navigation. She could visualize spherical trigonometry in 3 dimensions, seeing mathematical relationships between observer celestial bodies and geographic coordinates as geometric problems that could be solved through logical analysis. Her understanding of the mathematical principles allowed her to work faster and more accurately than navigators who followed standardized procedures without fully comprehending the underlying mathematics. She could see shortcuts and relationships that weren't obvious to people who relied primarily on published tables and mechanical calculators. The first position fix required nearly 40 minutes of intensive mathematical work. Sarah had to take multiple celestial observations, perform the complex calculations for each site, then solve simultaneous equations to determine the bomber's latitude and longitude. The mathematical complexity would have challenged most professional astronomers under ideal conditions. Her first position fix, completed at 12:15 p.m., showed the formation 23 miles south of planned track but maintaining correct speed toward the target area. The deviation was within acceptable limits and could be corrected with a minor heading change, but Sarah had no way to communicate the course correction without explaining she was using unauthorized navigation techniques. The accuracy of her position fix was remarkable considering the conditions under which she'd performed the calculations. Using only manual observations and mental arithmetic, she'd determined the bomber's position to within a few miles after flying blind for more than an hour over featureless ocean. But the mathematical work was physically and mentally exhausting. Each calculation required absolute concentration while performing arithmetic that would challenge most mathematicians under ideal conditions. Sarah was doing this work while flying in a combat aircraft approaching enemy territory, with the lives of 16 crews depending on her accuracy. Military regulations prohibited unauthorized modifications to navigation procedures, particularly during classified missions where deviation from approved methods could compromise operational security. Sarah's celestial navigation techniques weren't covered in any military manual and hadn't been approved for operational use under combat conditions. She decided to provide heading corrections as suggestions based on wind drift observations, letting the pilot believe she was using conventional dead reckoning navigation rather than revealing she'd abandoned standard procedures completely. "Major Morrison, I'm seeing stronger than expected wind from the north," Sarah called through the intercom. "Recommend coming left 5 degrees to correct for drift." The course correction worked perfectly. Sarah's next position fix, taken 30 minutes later, showed the formation back on planned track and maintaining schedule toward the target area. But the mathematical work was exhausting. Each calculation required intense concentration while performing mental arithmetic that would challenge most mathematicians under ideal conditions. The psychological pressure was enormous. Sarah knew that calculation errors could cause the mission to fail, resulting in the loss of 16 crews and America's most important bombing mission since Pearl Harbor. Every mathematical operation had to be performed perfectly, with no opportunity to verify her work except through subsequent observations. The responsibility weighed heavily on her as she continued taking celestial observations and performing the complex calculations required to convert them into position information. She was the only person in the formation who could determine where they were or provide heading guidance toward their targets. The formation was approaching Japanese airspace, where enemy fighters and anti-aircraft defenses would make navigation even more challenging. Sarah would need to maintain absolute precision in her calculations while the bombers flew through increasingly dangerous territory where any navigation error could prove fatal. Her mathematical techniques were working beautifully, achieving accuracy that exceeded the capabilities of electronic navigation systems available in 1942. But the physical and mental demands of performing complex calculations under combat conditions were testing the limits of human endurance and mathematical capability. The Japanese coastline appeared at 1:42 p.m., exactly when Sarah's calculations predicted landfall. The formation was within 2 miles of the planned coastal crossing point, demonstrating that celestial navigation could achieve accuracy comparable to electronic navigation systems under the right conditions. But reaching Japan was only the beginning. The bombers still needed to find specific targets in Tokyo, deliver bombs accurately, then navigate 1,200 miles across China to reach friendly airfields while flying at night through unknown weather conditions. The target area presented new navigation challenges Sarah hadn't anticipated. Tokyo was partially obscured by industrial haze and smoke, making visual landmark identification difficult. The bombers needed to find specific facilities within the sprawling urban area, then navigate to predetermined exit points that would minimize exposure to anti-aircraft defenses. Sarah had memorized detailed Tokyo maps during training, but navigating over the city required constant position updates using visual landmarks that might be obscured or altered since intelligence photographs were taken. She needed to provide continuous heading guidance to keep the bomber on course toward its assigned target. The bombing run began at 1:52 p.m. Sarah directed Major Morrison toward their assigned target, a military aircraft factory in northern Tokyo. The approach required flying through light anti-aircraft fire while maintaining precise heading control to reach the bomb release point. Sarah's navigation during the target approach was flawless. She guided the bomber directly over the aircraft factory, confirmed the target visually, then provided heading guidance for the exit route that would take them away from Tokyo while setting course for the flight to China. But the most difficult navigation was yet to come. The 1,200-mile flight to China would be conducted at night over mountainous terrain through potentially severe weather, with fuel supplies providing little margin for navigation errors. If Sarah's calculations were wrong by more than a few degrees, 16 crews would run out of fuel over hostile territory with no possibility of rescue. The flight to China began at 3:15 p.m. Sarah had calculated a great circle route that would minimize distance while avoiding known Japanese air bases, but the route required flying over water for 4 hours before reaching the Chinese coast. Navigation over water at night presented problems almost impossible to solve using 1942 technology. Without radar or electronic navigation aids, Sarah would have to rely entirely on celestial observations, taken through bomber windows, while flying through potentially cloudy skies that could obscure astronomical reference points. Sarah spent the afternoon preparing for night navigation by calculating positions of stars and planets that would be visible after sunset. She needed to identify celestial bodies, providing good geometric intersections for position fixing, determine their coordinates for different times during the night, and prepare mathematical solutions that could be computed quickly under difficult observational conditions. Night fell at 7:30 p.m., while the formation was still 300 miles from the Chinese coast. Sarah began taking stellar observations using her sextant through bomber windows, measuring angles between bright stars and the horizon to determine lines of position that would intersect at the aircraft's location. The observational work was incredibly difficult in the dark bomber interior. Sarah had to use a red flashlight to read her sextant without destroying night vision, record precise timing for each observation, then perform mathematical calculations by feel since she couldn't see notes clearly enough to verify arithmetic. But the stellar navigation worked beautifully. Sarah's position fixes showed the formation maintaining course and speed toward the Chinese coast, with arrival predicted for 11:45 p.m. The accuracy was remarkable, considering she was using manual calculations to guide 16 aircraft across 2,200 miles of ocean and mountainous terrain. The Chinese coast appeared exactly when Sarah's calculations predicted, validating her navigation methods under the most challenging conditions possible. But finding the specific airfield required even more precise navigation through mountainous terrain in complete darkness. Sarah had memorized topographic maps of the landing area, but navigating to a specific airfield required identifying landmarks invisible at night. She needed to use terrain features, river patterns, and city lights to guide the formation to an airfield that might not have navigation aids or runway lighting. The approach required flying through mountain passes barely wide enough for safe passage, then descending to an airfield in a valley surrounded by peaks rising above the bomber's cruising altitude. Navigation errors of more than a few miles could result in controlled flight into terrain, destroying the entire formation. Sarah's navigation during the final approach was perfect. She guided the formation through mountain passes using visual references and dead reckoning calculations, then provided precise heading guidance to the airfield that appeared exactly where her calculations indicated. The landing was completed at 11:52 p.m., 7 minutes later than Sarah's predicted arrival time. After flying 2,400 miles from the carrier task force to Tokyo to China, using navigation methods no one had attempted under combat conditions, she had achieved accuracy exceeding the capabilities of electronic navigation systems. 16 bombers had successfully completed the most ambitious bombing mission in military history. Every aircraft reached its assigned target, delivered bombs accurately, then navigated safely to China, despite equipment failures that should have made the mission impossible. But Sarah's navigation achievement remained classified for security reasons. The success of the Doolittle Raid was attributed to superior planning, crew training, and aircraft performance rather than innovative navigation techniques developed under combat conditions. The other navigators in the formation had struggled with compass failures but managed to follow Sarah's lead aircraft to their destinations. None realized their successful navigation had depended entirely on celestial calculations performed by someone using techniques not covered in any military training manual. Sarah continued flying combat missions in the China-Burma-India theater for the remainder of 1942, developing navigation techniques for operations where traditional navigation aids were unavailable. Her methods became standard procedure for long-range bomber operations, though her contributions were rarely acknowledged officially. After the war, Sarah completed her doctorate in mathematics at Stanford, focusing on navigation theory and mathematical foundations of position fixing using astronomical observations. Her dissertation incorporated lessons learned during combat operations, providing theoretical frameworks for navigation techniques developed through practical necessity. She joined Stanford faculty in 1947, becoming one of the first Chinese-American women to hold a professorship in mathematics at a major American university. Her research focused on navigation mathematics, stellar astronomy, and computational methods later incorporated into early electronic navigation systems. During the 1950s, Sarah consulted for the military on navigation systems development, helping design mathematical algorithms that would guide intercontinental ballistic missiles and early satellite navigation systems. Her work on spherical trigonometry and celestial mechanics provided theoretical foundations for technologies that wouldn't become operational until decades after her original innovations. But Sarah rarely discussed her role in the Doolittle Raid during her academic career. The mission remained classified, and her specific contributions weren't publicly acknowledged until military historians began studying navigation aspects of the raid in the 1970s. When asked about wartime service, Sarah would say she'd been a navigation instructor who helped train bomber crews for Pacific operations. She didn't mention that she'd personally guided 16 aircraft across 2,400 miles of ocean and hostile territory, using mathematical calculations that had never been attempted under combat conditions. In 1982, 40 years after the Doolittle Raid, military historians contacted Sarah about her navigation methods. They were researching technological innovations that had contributed to Allied victory and discovered references to unauthorized navigation techniques used during the Tokyo bombing. Sarah agreed to one interview about her navigation methods on condition the information wouldn't be published until after her death. She didn't want recognition for breaking regulations, even when violations had been necessary for mission success. The interview revealed the full extent of Sarah's mathematical achievement during the Doolittle Raid. Military historians realized the mission's success had depended entirely on navigation calculations performed manually under combat conditions, using techniques that exceeded contemporary electronic systems' capabilities. Sarah's navigation during the Doolittle Raid represented one of the most significant achievements in military aviation history, demonstrating that individual expertise could overcome technological limitations when human knowledge was applied creatively under extreme pressure. Dr. Sarah Chen died in 1995 at age 77, survived by her husband and 2 children who had followed her into academic careers in mathematics and engineering. Her obituary mentioned her distinguished academic career and wartime service as a navigation instructor, but made no reference to the Doolittle Raid. Her personal papers, donated to Stanford after her death, included detailed calculations from the Tokyo mission showing mathematical methods she'd used to guide the bomber formation. The papers demonstrated extraordinary complexity of her navigation work and remarkable accuracy achieved using manual calculations. In 2002, the Smithsonian Institution created an exhibit about technological innovation during World War II that featured Sarah's navigation methods alongside other examples of creative problem-solving under combat conditions. The exhibit was the first public recognition of her specific contributions to the Doolittle Raid's success. The exhibit included reproductions of Sarah's mathematical calculations showing spherical trigonometry equations she'd solved manually while flying through hostile airspace. Visitors could see the complexity of navigation work performed without electronic computers or modern calculators. But perhaps more importantly, the exhibit demonstrated how individual expertise and creative thinking could achieve results exceeding contemporary technology capabilities when knowledge was applied intelligently under pressure that would challenge even the most experienced professionals. April 18, 1942. 16 bombers flying blind over the Pacific Ocean with every navigation instrument rendered completely useless by magnetic storms that couldn't be predicted or compensated for using available technology. One mathematician with a sextant and extraordinary mathematical ability, calculating precise courses and positions using theoretical techniques that hadn't been attempted under actual combat conditions. Sarah Chen proved that sometimes the most sophisticated technology is the human mind applied creatively to seemingly impossible problems. Her navigation during the Doolittle Raid achieved accuracy that exceeded electronic systems while demonstrating that mathematical knowledge could overcome technological limitations when lives depended on absolute precision. The raid succeeded not because of superior equipment or extensive training, but because one person refused to accept that equipment failure meant mission failure and certain death. Sarah's mathematical calculations guided 16 crews across 2,400 miles of hostile territory and brought them home safely when conventional navigation would have failed completely. Her achievement represented more than successful navigation under impossible circumstances. It demonstrated that determination, mathematical expertise, and creative problem-solving could overcome seemingly insurmountable technological challenges when human lives depended on finding solutions rather than following failed standard operating procedures that had become useless under combat stress. Sarah's innovations during the Doolittle Raid influenced military navigation procedures for the remainder of World War II and provided theoretical foundations for electronic navigation systems that wouldn't be developed until decades after her original mathematical breakthroughs under combat conditions. Her techniques proved that human intelligence could exceed the capabilities of contemporary technology when applied with precision and creativity. The mission's success demonstrated that individual expertise could achieve results that seemed impossible using conventional methods. When military equipment failed under the stress of combat operations, mathematical knowledge and human determination provided solutions that no electronic system could have matched under similar circumstances. But perhaps most significantly, Sarah's achievement proved that breakthrough innovations often come from individuals who refuse to accept conventional limitations and apply their knowledge creatively under extreme pressure. Her navigation techniques saved 16 crews and contributed to a mission that changed the course of the Pacific War through mathematical precision applied under combat conditions. 2,400 miles of vast ocean and hostile enemy territory, covered through incredibly precise mathematical calculations performed under seemingly impossible wartime conditions, yet 16 aircraft guided by celestial navigation performed manually under extreme combat conditions that would challenge even the most advanced modern electronic navigation systems available today. And the profound realization that human expertise and mathematical knowledge matter far more than advanced technology when applied with absolute precision under extreme pressure that would overwhelm most people completely and absolutely in similar circumstances.